In this section, we're going to talk about optimization problems. Another way to think of these is what we call applied maximum and minimum applications. An optimization problem is one in which you are tasked with finding a maximum or a minimum value, or where that value occurs. To solve an optimization problem, this is a lot like a word problem, so some of the steps are very similar. Obviously, you should read the problem first, and then reread it to figure out what information you're being asked to find, what information you're given, and how that information relates. But for an optimization problem, you should also start by drawing a picture. In many cases, you're going to be looking at something that you can represent pictorially. If you can't, oftentimes there's going to be some relationship of the variables, so you should be able to find a way they relate. For a lot of our business applications, that would be things like when the cost and the revenue are put together to come up with your profit, or when I have variable and fixed cost to come up with the total cost. So there's always going to be some way to relate the variables, whether it's with an equation, a formula, or a picture. Next thing you want to do is set up the function to be optimized. So depending on what you're asked to find, if I want to find the minimum cost or the maximum revenue, or maybe even the minimum area, that is always going to tell me what it is I need to optimize and what equation I'm going to need. So in the case of a minimum cost, I need to figure out what my cost function is. In a maximum revenue, I would figure out what my revenue function is. Okay. Once I have my function, I want to make sure I express it in terms of one variable. Many times your equations or your pictures will give you multiple variables to put together, and you need to find a way to get that in terms of one variable. If you think about all the derivatives we've done, they all are in terms of one variable up to this point. Okay. Once I have the function, then I want to note the domain. And this is important because sometimes you're going to get equations where the domain is all real numbers. But again, when I look back in terms of the problem, some of those real numbers may or may not work. So I want to note the domain of the function. And in this case, I do mean the practical domain. What makes sense in the problem, but also makes sense for the function. Okay. Once we have the domain, now we're going to take the derivative. And then we want to use that derivative to find the critical values. So where are the possible extrema for my function? And then once I have those possible ones, I'm going to test for the extrema. And so we've talked about the first derivative test and being able to use that to determine where maxes and mins occur. In this section, I'll talk about some other methods that will come up later, and we'll look at those as well. Okay, so test for extrema. Once I have my extrema, so once I know it's a max or I know it's a min, state your solution. And this just means not just giving me the number that gives me that maximum value, but make sure I answer all the parts of the question. Some of your problems are going to ask for you to find that maximum where it occurs and then also find the maximum value. Or it'll ask you things like, you know, once I have the max, where is the point that makes it break even, or where, things like that. So make sure you actually answer the questions that are asked in the problem. Okay? So let's look at an example. So this is a fairly straightforward one of your business applications, and many of these will be similar to this, where they already give you the function, but not all of them will. Okay? So in this one, we have a demand equation for a manufacturer's product, P equals 80 minus Q over 4, where Q is between 0 and 80. And we want to find the number of units that will give a maximum revenue. Q is the number of units, P is our price, and once we find that Q value, we want to also determine what the maximum revenue is. Okay? So for this one, I can't really draw a picture for this, but I can use an equation to relate my variables. So again, I know that I want to find a maximum revenue, which means I need a revenue function. And we know that revenue is basically price times quantity. Okay? Again, in this case, I have two variables, so I want to get it in terms of one variable. In a case like this where you have more than one variable, you want to make sure you get it in terms of the right variable. So here, because I'm trying to find the value for Q, I know I want Q to be my value here. So here I'm going to replace P with 80 minus Q over 4 and multiply that by Q to get my revenue. Okay. Again, we should note the domain. Here again, this one is fairly nice because they give us the domain. Our domain for our revenue is in terms of Q, and Q is already told to be between 0 and 80. And in this case, this is inclusive. Okay, so I know if I get values outside of that range, then they can't be solutions to this problem. Okay. Now that I have my function and its domain, I need to find my critical values. So to find my critical values, I'm going to take the derivative. So here, notice that 4 on the bottom, there's no Q. So I can actually just move that out front and take the derivative of the numerator. Okay, simplifying that down, there's my R prime. For my critical values, I want to look for where it's 0 and where it's undefined. So notice R prime equals 0 when 20 equals a half Q, or Q equals 40. If I notice this one, R prime is never undefined. So in this case, I just happen to have a nice polynomial function, so I don't have to worry about the undefined portion. Using my number line, I'm going to put my one critical value on there and test points on either side. Okay, so some good test points in this case, 1 and 50. And notice my test points I'm picking are also within my domain. Okay, so plugging 1 into my equation, I see I get 20 minus a half. That is certainly going to be a positive value. And if I put 50 in there, I get 20 minus 25. That is certainly going to be negative. So we can see that it's increasing and then decreasing, which means this is going to be a max, which is what I wanted to find. So I wanted to maximize the revenue and find the maximum revenue. This value here is my Q that gives the maximum revenue. Okay? But I still have to find the maximum revenue. So at this point, I'm going to go back to my revenue equation and plug in that value that I got for Q. So 80 minus 40 all over 4 times 40. Looks like 40 over 4, or 10 times 40, which is 400. Okay. Lastly, state your solution. So in this case, my solution is when there are 40 units, the max revenue is $400. In this next example, we will look at another max-min optimization type problem. So here we're given, for insurance purposes, a manufacturer plans to fence 10,800 square feet of a rectangular storage area adjacent to a building. He wants to use the building to enclose one side of this area. The fencing parallel to the building faces a highway and costs $3 per foot, while the other sides cost $2 per foot. We want to find the amount of each type of fencing so that the total cost will be minimized, and then find the minimum cost. Okay. So again, in this type of problem, we want to start by coming up with our function. A good way to do this is to start by drawing a picture. So in this case, here's our building. And we want a rectangular lot adjacent to it, where one side of the lot is bounded by the building. Okay. They tell us that the fencing parallel to the building is $3 per foot, and the other sides are each going to be $2 per foot. So if we're looking at our picture, we can label our sides. Let's call the smaller sides X and the larger side Y. Okay. Now let's use this to come up with our information so that we can formulate a function. So the other piece of information that they give us is that 10,800 square feet is going to be covered. So we know that X times Y has to equal 10,800, and we are trying to minimize the cost, which means I need a cost function in order to take my derivative. So my cost function is basically going to come from the side length times the amount per side length. So we're going to have 3 of the side Y, so $3 for each square foot for the longer side, plus 2 of the $2 per square foot for the shorter sides. Okay, there would be our costs. Okay. So now that we've got our picture that gave us our function, we want to get our function in terms of one variable. And in order to do that, we can use the relationship between X and Y in our area formula. So we can see here that Y is going to be 10,800 divided by X. Okay. So our cost equation in terms of X is going to be 3 times that Y, so 3,2400 over X plus the 4X. Okay. Again, we should note the domain. So our domain for the cost function, well, X cannot equal 0, which makes sense here as well. If X is 0, then we don't get a rectangle. But it could be as small or as close to 0 as we like. So it's going to go 0, and then up to, well, we do have a bound on this. So again, for as small as our Y can be, our X at most can be 10,800. Okay. So now we've got our function and the domain. So to minimize this, we're going to look at the derivative. So using our properties here, we can see this is going to be negative 3,2400 over X squared plus 4. So here we need to find our critical points. And in order to find our critical points, we need to set 32,400 over X squared plus 4 equal to 0. We can see it's undefined at 0, but again, that's not in our domain, so we can exclude that point. From here, we just solve. So 32400 over X squared is going to equal 4. So moving that to the other side, multiplying by our X squared. We can divide out by 4. And take our square root of both sides. Okay. Notice here I don't put the plus or minus, and that's again because we know our domain is positive. So here, X equaling 90 is one of our critical points. Now with the X equals 90, we can't necessarily say that's a max. We still have to check that, or a min. And in this case, we're looking for a min. So we need to use some sort of derivative test to determine whether that's a max or a min. Okay. In this case, our derivative is nice enough. We could do a second derivative. So C double prime is going to be 648 with 2 zeros over X cubed. That term is going to go to 0. We can see C double prime of 90 turn out to be this number. Again, I don't care so much what this number is. All I care is that this is positive. So this tells me I'm looking at something that is concave up, which means we have a min. Okay. So now we need to go back and answer our question. We need to find the amount of each type of fencing so that the cost will be minimized. So in our picture, we said that x is going to be 90. We still need to find y. So x times y was 10,800. So 90y is 10,800, or y equals 1080 over 9, which, if we look, is 120. Okay. So there's our dimensions. Okay. And to find the minimum cost, we can again plug those back into the function. So C of 90 is going to equal go ahead and simplify. Okay. And of course, lastly, once we get this information, we want to state our solution. So, our solution says the dimensions are 90 feet by 120 feet, and the minimum cost is going to be $720. So let's look at another example of optimization. In this example, the Vista TV company currently has 100,000 subscribers who are each paying a monthly rate of $40. A survey reveals that there will be 1,000 more subscribers for each 25% decrease in the rate. At what rate will the revenue be maximized, and how many subscribers will it be? Okay. So this is another one where I can't exactly draw a picture, okay? But we can use the information to come up with an equation. Here we are looking to maximize revenue, and we know revenue is price times quantity. So I just need to think, if I'm looking in the future and I decrease the rate, how many subscribers or how much revenue will I be bringing in per subscriber? Okay. So here, let's look at our revenue equations. So R will equal our price times our quantity. Okay. Our current price is $40, and we know for each 25-cent decrease, I'm going to basically increase my subscribers. So let's let X be the amount of the number of decreases we have. So there would be my price for X number of decreases. Likewise, for my quantity, I know I currently have 100,000. And for each of these decreases, I'm going to gain 1,000 more subscribers. Okay, so there would be my revenue function. Okay, my revenue function is already in terms of one variable, so I just need to go ahead and find the critical points. Now here you can multiply this out, but this is a good instance of where my product rule makes it a little bit easier. I don't have to FOIL this out with these large numbers. I can just use my product rule. So my derivative, R prime, is going to look like the derivative of the first, which is negative 1/4, times the second, 100,000 plus 1,000x, plus the first, times the derivative of the second. Here I can clean that up some. So R prime is going to equal, well, taking that divided by 4, it's going to be 225,000. It's a negative out front. Minus 250x. Over here multiplying out, plus 40,000 minus 250x. Okay. So our R prime is going to look like a minus 500x plus 15,000. Okay. Now that I have my derivative, I can find my critical points. So polynomial function, I know it's not going to be undefined anywhere, so I just need to look for where it's 0. So negative 500x plus 15,000 is going to equal 0 when 15,000 equals 500x. Dividing by the 500 looks like 30. Okay. All right, so there's our x. We need to determine if that critical point is a max or a min. Okay. So using my number line, I'm going to pick some points in each region. Now here, I didn't really talk about what the domain is, but let's look at that for just a second. In this case, our function is polynomial. If I'm looking here, it's a polynomial function, so domain is necessarily all real numbers. But again, I can't have a negative number of subscribers, so I know that decrease is not going to work if that's a negative value. So here I can see that x has to be bigger than 0, and from this statement here, it's got to be less than 160. Because once I'm past 160, this becomes a negative value, and I'm getting negative revenues in there. Okay, so for my domain, I can think it's got to be between those values there. So my test points, I'm just going to pick something in each region. Let's say 1 and 40. Okay. Plugging into my derivative. So when x is 1, we can see 15,000 minus 500 is certainly going to be positive. And when I plug in 40, we get negative 20,000 plus 15,000, so that's going to be negative. So we're increasing and then decreasing, so that is a max. Okay. From there, now that we know x equal 30 gives the max, we can use that to find the maximum revenue. So plugging in, we can see 40 minus 30 over 4, 100,000 plus 30,000. Okay. Getting a common denominator in that first bit, multiplying by 4, we get 160 minus the 30, so 130 over 4 times 130,000. Okay. Dividing out by 4, we'll get 32.5 times 130,000. And multiplying this out, we'll get $4,225,000 for our revenue. Okay, let's look at one last example. Suppose the demand for a certain product is P equal 400 minus 2Q. The average cost, C bar, is 0.2Q plus 4 plus 400 over Q. We want to find the number of units to maximize the profit, determine the price at this value, and determine the maximum profit. Okay. So for this one, we have most of our information set up for us. If we look, we want to maximize profit, and they give us a demand and an average cost. So here again, remember, profit is revenue minus cost. So to get our revenue, we need our demand times quantity. And for cost, we need our average cost times quantity. Okay. So our profit equation is going to be 400Q minus 2Q squared minus our C bar times Q. So 0.2Q squared plus 4Q plus 400. And again, watch your signs on these. Okay. Here, if you want to go ahead and combine terms and make this a nice polynomial, we get negative 2.2Q squared. There's a 4 and a 400, so plus a 396Q minus 400. Okay. Domain for this one, Q cannot be 0, so because of our denominator there. And then if we look, well, Q can basically go up to 200, because once it's past 200, our demand here becomes negative. Okay, so domain for P is going to be 0 to 200. Okay. Let's look at our derivative. So again, from here we need to get our critical points. So looking at our derivative, we get a negative 4.4Q plus a 396. So now we just need to determine where the critical points are. So notice, again, it's a polynomial function, meaning P prime is never going to be undefined. So we just need to determine where P prime is equal to 0. And that's going to occur when 4.4Q is equal to 396, or when Q is equal to 90. Okay. Once we have our value, again, we just need to test. So putting this on our number line and picking points, again, we need to be between 0 and 200. So let's pick, say, 110. Okay, again, pick any values you like, but just make sure they're within range. So plugging this into our derivative, we can see at 10, we're going to get a negative 44 plus a 396. So that is certainly going to be positive. At 100, we're looking at a negative 440 plus 396. So that's certainly going to be negative. So it's increasing and then decreasing, which tells us this is going to be a max. Okay. Now, this is our Q value, and we were asked to find a couple different things. So when stating our solution, we just need to go back to our problem and make sure we've answered all the pieces. Okay. So in particular here, we want to find the number of units to make the maximum profit. So at 90 units, the profit is maximized. We want to determine the price at this value. Well, we just need to plug back into our demand equation. So when Q is equal to 90, we can see that P is going to equal, so plugging in 90, we get 180, taken away from 400, looks like $220. Okay, so there's our price. That's going to give us the max profit. And then lastly, we want to determine the maximum profit. Okay, so once I know my P and my Q, we can plug back into our equation here. Okay. So plugging into our P equation, we can see putting in 90 here, we'll get 17,420.